guys, my name is IBM and I'm still taking you through kinematics. I'm still taking you through kinematics. Remember, in lesson 1 and lesson 2, I think we described the motion where we talked about speed and velocity, we talked about acceleration, we talked about distance and displacement. In lesson 2, I think we talked about we described the motion using graphs. We saw the displacement time graph, the distance time graph, the velocity time graph, the acceleration time graph, and so on and so forth. So we saw that in lesson 2. So in lesson 3, I want us to talk about uniformly accelerated motion. Remember, in uniformly accelerated motion, the most important thing is going to be the equations of motion. Maybe in lesson 4 we shall talk about, in lesson 5 I think we shall talk about projectiles. And I said all this is mechanics. All this is mechanics. So this is AS Physics and this is going to be lesson 3. So let us start with a uniformly accelerated motion, or basically we shall be talking about equations of motion. So we are going to look at uniformly accelerated motion in a straight line. So using the definitions of displacement, remember displacement was distance in a specified direction, or the direct distance, the shortest distance from one point to another point, or the straight line distance from one point to another point. And using definitions of velocity, we said velocity was the rate of change of displacement, and acceleration was the rate of change of velocity. So for using the definitions of displacement, velocity, and acceleration, we can derive a series of equations that we are going to call the kinematic equations, or equations of kinematics, which can be used to give a complete description of the motion of a particle in a straight line. So these equations, we are going to use them on only objects which are traveling or moving in a straight line. That's number 1. And number 2, these equations are going to be used for objects moving with a uniform acceleration. That is the second important thing. So from the definitions of displacement, velocity, and acceleration, we are going to derive what we call kinematic equations. And these are going to be used to completely describe the motion of a particle in a straight line. So let's consider a particle moving along a straight line with a constant acceleration, call it A. Suppose at time t equals to 0, that is initially the velocity at time t equals to 0 is going to be called u. Then after some time, let's say after some time t, the velocity now is increased to v. So it means there is a change in velocity. And from the definition of acceleration, as the rate of change of velocity, it means we have that the acceleration is equal to v minus u divided by t. If I try to rearrange this equation, I obtain that v equals to u plus at. So that is the first equation of kinematics. The first equation of kinematics. Now, this equation will only be used to describe motion if the body is moving in a straight line. Number 2, if the acceleration is constant. So, like I said, we are going to use the definitions of velocity, displacement, and acceleration to derive the equations of motion. And we have so far derived the first equation. V equals to u plus at is the first equation of motion, or the first equation of uniformly accelerated motion, or the first equation of kinematics. That's number 1. Okay, so for starters, this is going to be the first equation of motion. V equals to u plus at. We just got it from the definition of acceleration as the rate of change of velocity, where we got final velocity minus initial velocity divided by time, and we just rearrange the equation and we got v equals to u plus at, where a is acceleration, which must be uniform or it must be constant. Okay. Now number 2. So now let's consider a different kind of motion. So we can also find these equations. We can also find the same equations from what we call the velocity time graph. Let's consider the velocity time graph shown here. So consider the velocity time graph shown here. In this velocity time graph, you will notice that the velocity is increasing. At t equals to 0, the velocity is u, and at t, after a certain time t, the velocity is equal to v. So if I wanted, of course, the acceleration would be v minus u divided by t, which would give me v equals to u plus at. However, I want you to notice that if I try to look at the motion of this body from t equals to 0 to t equals to t, I will just consider the straight line up to this point here. If you look at the area under this line, here, we can divide this into two parts. We have a rectangle at the bottom and we have a triangle. For the rectangle, on the vertical we have u, on the x-axis we have t, so the area of the rectangle is u times t. Then we have a triangle. The area of the triangle is going to be a half times t because this is a triangle. On the x-axis, you have t. On the y-axis, you have v minus u. So because remember from the first equation, we saw that v was equal to u plus at. So this vertical distance here is v minus u. But we know that v minus u is the same as at. So on the vertical is v minus u, which is the same as at. So if I try to find the area was a half times times t times v minus u, which is the same as a half times t times 80. That's why the area of the triangle is a half 80 squared. If I try to find the gradient of this graph, I want to erase some of these things to make this space interestingly nice. If I try to find the gradient of this straight line, remember the gradient of a velocity time graph is the acceleration. So if I try to find the gradient of this line from t equals to 0 to t equals to capital T, if I try to find the gradient, so I will have that the gradient is the same as the acceleration. So the gradient is going to be changing v over the time, which will be v minus u divided by t. That is, of course, the gradient. Of course, the gradient is the acceleration. So from this, we can come back to what we have already derived, that v is equal to u plus at. So let's first concentrate on just using the gradient to derive v equals to u plus at. So I have just mentioned that the gradient of the straight line is constant and is the acceleration. And we have said that the gradient is going to be equal to v minus u divided by t in that case, which still takes us back to v equals to u plus at. If I just find the gradient, v equals to u plus at. However, I want you to notice from what I've just discussed or what I've just mentioned earlier on, if the gradient is equal to v plus minus ut, if the gradient is equal to v minus u plus at, I can also obtain the area under this graph and see what I obtain. If I try to find the total area under this graph, you'll notice that the area under that graph would be equal to the area of a triangle, which is a half into a t squared plus the area of the triangle, which is u times t. But remember from what we have already discussed earlier on, the area under the graph of a velocity time graph was the displacement. So it would be easier for you to see that s, which is the displacement, would be ut plus a half at squared. So this will also be another equation, or the second equation of motion, where the acceleration must be constant and the object must be moving in a straight line. So if I just found the area under that graph and The area of the rectangle at the bottom was ut. The area of the triangle was a half at squared. So if I find the total area, it would be ut plus half at squared. You could also take this as a trapezium, and the area of a trapezium would still be, of course, the area of a trapezium from mathematics is a half into a plus b times the height h. So one side will be a, so this will be a half, a would be maybe u, and b will be maybe v. So this will be a, the other one will be b. If I take it as a trapezium, and this will be the height h. So this will be times the height h, which is going to be t. So remember, the area is still the displacement. So I can also have the displacement as equaling to a half into u plus v times t. So the displacement could be given by this equation. It could also be given by that equation there. Area under the graph, if you take it as a trapezium. So someone may be asking, how does a half into u plus v t become ut plus a half at squared? Of course, you just use the first equation and remove a v. If v is equal to u plus at, if v is equal to u plus at, s would be equal to a half into u. Where there is v, I'm putting u plus a t. Then I multiply this by t. So this becomes, there is 2u plus at squared, 2ut. So this is a half into 2ut plus at squared. So this still takes you back to ut plus a half at squared. So it's the same thing. So we have s is equal to ut plus a half at squared. S is equal to a half into u plus v times t, which is still the same equation as before. So far we have now three equations. Even though the second equation and the third equation are almost the same, we just modified one to get the other one. So these are called equations of motion. These are called equations of motion. Okay, of course, by the way, I can modify s equals to a half into u plus v times t, and maybe I could remove t. So from the first equation, let me try to remove t to show you that it's easier to derive these equations, even though you may not be asked to derive them, but it's very easy to derive them. If you have the first equation, you have a straight line, it is easy to derive them. So let me see if I have v equals to u plus at. So v equals to u plus at. This implies that arrow, this symbol is for implying that t is going to be v minus u divided by a, that is t. So from s equals to a half into u plus v times t. Where there is t, I'm going to put there v minus u over a. So this becomes a half into u plus v. Where there is t, I'm putting v minus u over a. A math student should be seeing a difference of two squares here. So this is going to be a half. There's an a here, but you see u plus v times v minus u is a difference of two squares. Or maybe someone who is not doing math may not see it as a difference of two squares. I will just multiply. So this will be, if I open the brackets, there's an a in the denominator. So I have this as uv minus u squared plus v squared minus uv. So uv has cancelled out. So this means I have that s equals to a half 1 over 2a into v squared minus u squared. If you arrange this, you have 2as equals to v squared minus u squared. Or if you continue to rearrange, you'll have v squared as being equal to u squared plus 2as. So I have derived the last equation, and this is a very important equation. So we can derive equations as long as we know the first equation from the gradient. We know that from the area under the graph, we can find the displacement. And from the displacement and the first equation, we just use algebra and find the last equation. Okay, there could be another way of actually obtaining this. I could show another way of obtaining this. So alternatively, we are going to consider a different situation or a different graph like this one here. Let's consider a graph like this one. So this is also a velocity time graph. And we know that the displacement is given by the area under the graph. So the object's average velocity in this case is going to be halfway between v and u. So if we consider the motion, if we consider the velocity time graph like this one here, then we know that if the velocity increases from u to v in a time t, then the average velocity of this is going to be halfway between these two. And what is the average velocity? Of course, we know that since it is halfway, it is going to be u plus v divided by 2. That is going to be the average velocity of this motion. So the average velocity is going to be given by v plus u divided by 2. That is the average velocity. Remember, the displacement is given by the area under the velocity time graph, and we are observing that the object's average velocity is halfway between u and v. So the object's velocity can be calculated by averaging the initial velocity u and the final velocity. Therefore, we get the initial plus the final divided by 2 because this is a straight line. Whenever we have a linear relationship, then the average can be the minimum plus the maximum divided by 2. And if that is true, the displacement S is going to be the shaded area. This is actually a rectangle. So someone will say, how about this other area here? How is it a part of the displacement? This area here is compensating for this one, which has not been shaded. This area here is compensating for this one, which has not been shaded, because this area is the same as this one. So there are two ways I would take this. Instead of finding the area of the rectangle, then I would just find the area of the triangle as we have done in the previous slide, plus the area of the triangle plus the area of the rectangle. However, I'm saying the displacement in this case can also be the area of the rectangle for the whole of this shaded part. Yet we know that the displacement is supposed to be the area under the graph. Yet the other part, this part here, is above the line. But I'm saying this part which is above the line is compensating for this part which is below the line. So it is as good as simply taking the area under the rectangle, or the area of the rectangle which is indicated here. So it means the displacement is going to be equal to the area under the rectangle. So we shall have the displacement as the average velocity, which is going to be, of course, the average velocity is u plus v divided by 2, then times time. Because the area under the rectangle at this point here, the velocity here is v plus u divided by 2. So the vertical is v plus u divided by 2, and the horizontal is t. So it is the average velocity times the time that is going to be the displacement. So this gives us s equals to u plus v divided by 2 times t. And when you rearrange this, or when you just make it modified, we get s equals to a half into u plus v times t. And I say that was the second equation, or the third equation, whichever order you put them. But alternatively, I said, instead of, if that is hard to see that the displacement is the area under the rectangle or the area of the rectangle, I just showed to you that we could, instead of considering the average velocity in that case, we could just consider this. We could just consider the displacement as the area under the line, this line here with the x-axis, where this is going to be our A, that is u, and this is going to be our B, which is V, and this is going to be our H, which is T. So the area, the displacement is the area under the graph or under the line, which is a trapezium, and the area of a trapezium is a half into A plus B times H. So this will be a half. A is U, B is V, and H is T, which automatically gives us that simple equation for the displacement. So then what remains is just to modify this equation to get a third important equation that we may always need in our calculations. Do not forget these equations are going to only be used for uniformly accelerated motion. So when we try to modify the equation we have just obtained, we have obtained that the first equation was V equals to U plus AT. The second equation was S equals to a half into U plus V times T. We can modify those equations to get whatever equation we want. So if I get the first equation and I put it into the second equation, in other words, I'm putting V in the second equation. So S becomes, where there is V, I've put there U plus AT. And when you simplify, you get a half UT plus AT squared. So which gave us S equals to UT plus half AT squared. And that can be the third equation. The order of these equations or numbering them may not really matter. A few things we need to note from what I've just derived. Number one, the right-hand side of this equation is the sum of two terms. You notice that is the sum of UT plus a half AT squared. This is a term and this is also a term. So the UT term is the distance the particle moves if the velocity is constant. So is the distance the particle would have traveled in time t if it had been traveling with a constant speed u. If it was to travel with a constant speed u, then it means the acceleration would be zero. So the UT term is the distance it would cover. And this a half AT squared term is the additional distance it traveled because of the acceleration. So the first term is the distance it would travel if it was moving at a constant speed. And the second term is the distance it travels if, or it is the distance it travels because of the acceleration, because it accelerates. So that's why we have those two terms, and it is very important to note them. Okay, so from this again, from the two equations, V equals to U plus AT and S equals to a half into U plus V times T, we have again derived the last equation. So let me just emphasize that again. So from the equation, V equals to U plus AT, if I made T the subject, T was equal to V minus U over A. And if I substitute that in the equation, S equals to a half into U plus V times T. I'm just going to remove T. So substituting that equation into equation 2, which was S equals to U plus V times T, we have that S equals to a half into U plus V. Where there is T, I'm putting V minus U over A. And when I do the algebra, I get 1 over 2A into U plus V into V minus U. And I've tried to show you this, that this is the same as a half times A, 1 over 2A into UV plus or minus U squared plus V squared, then minus UV when you just multiply those two. And when you expand this, it becomes 1 over 2a into uv cancels out. So you remain with the v squared minus u squared. So this gave us s as half 1 over 2a into u plus v times that, which boils down to 2as equals to v squared minus u squared, because if this is s, we cross multiply, you get 2as equals to v squared minus u squared. And hence, when you rearrange that equation, you get v squared equals to u squared plus 2as. So this is the last equation of kinematics. V squared equals to u squared plus 2as. In summary, these four equations are going to be called the Sauvert or the Sauvert equations many times. We saw that V equals to U plus AT, S equals to UT plus a half AT squared, and V squared equals to U squared plus 2AS, S equals to U plus V over 2 times T. I think in the list of formula of AS and A-level physics, I think these two are always stated. I think these two are always quoted in the list of formula. The first one and the last one may not always be quoted, but you can always use them, or you should always be able to use them. So I'm saying these ones are going to be called the Sauvert equations. So every time someone is talking about Sauvert equations, they're called Sauvert because you see they relate S, displacement, initial velocity, final velocity, acceleration, and time. That's why we call them the Sauvert equations. They relate displacement to initial and final velocity, acceleration, and time. Okay, so those are the equations of motion. So you can only use these equations only if the acceleration is constant or uniform. And by the way, that may not be the only reason as to the only condition for you to use them. The motion must be in a straight line. Motion must be in a straight line. The motion must be in a straight line. The acceleration must be uniform for us to use these equations. So every time you see me using them in the next examples, just know I have assumed the acceleration is uniform and the motion is in a straight line. Acceleration uniform, motion in a straight line. That's when I will be using these equations, which are called the Sauvert equations. So when you practice a lot, these equations become part of you, and you don't need to worry about solving questions or solving anything which requires you to use those equations, the so-called Sauvert equations. As long as you know the first and last equations here, you can always easily recall or use them in any calculation. Okay, let me try to use them, even though I normally don't do this in my class. I always leave students to use them and find answers because I just quote answers for my students. So where possible, I will give a hint. When it is very easy, I will not solve it. A car increases its speed from 25 meters per second to 31 meters per second with a uniform acceleration of 1.8 meters per second squared. How far does it travel while accelerating? So how far, that is distance. How far does it travel while accelerating? So because it's a uniform acceleration, then the equations of motion, the Sauvert equations, can apply. So you must know the three or the four equations so that you are able to know which one to use easily. We have the initial velocity, called this one u, the final velocity, called this one v, and we have the acceleration. So from the four equations, v equals to u plus at. That will not give us the displacement, it will only give us time. We have v squared equals to u squared plus 2as. V squared equals to u squared plus 2as. That will give us the displacement, so I'll use that one. So v squared equals to u squared plus 2as. The only thing which is missing here is the displacement. So the displacement s is going to be equal to v squared, which is 31 squared, minus u squared, which is 25 squared, divide by 2as. So I'm divide by 2a, so divide by 2 times 1.8. So what is S? I am just making S the subject by substitution here. So 31 squared minus 25 squared divided by 2 times 1.8. So this is giving me 93.3 meters. You can also check that. The average acceleration of a sprinter from the time of leaving the blocks to reaching her maximum speed of 9 meters per second is 6.0 meters per second squared. How long does she accelerate? What distance does she cover? So I'm not going to solve all these equations. I'll just give you a hint. They gave us the acceleration. Leaving blocks, it means initial velocity is equal to 0 because it's just leaving the blocks. So it starts from 0 velocity until it reaches 9.8 meters per second. For how long does she accelerate? So for the first one, I can use V equals to U plus AT. This is V is 9. So this means T is going to be 9.0 minus U, which is 0, divided by the acceleration, which is 6. So I'm just going to say 9 divided by 6. That is 1.5 seconds. Then what distance does she cover in this time? So the distance, because the acceleration is uniform, I can use V squared equals U squared plus 2AS. V squared equals U squared plus 2AS. Final velocity is 9, initial velocity is 0. So it means S is going to be 9 squared minus 0 divided by 2 times 6. So 9 squared divided by 2 times 6. So this is giving me 6.75 meters, and so on and so forth. So you can already solve those such questions. So I'll not solve all of them. A cricketer throws a ball vertically upwards into the air with an initial velocity of 18. So this is U. How long does the ball go? How long is it before it returns to the cricketer's hands? So, of course, if it reaches the highest point, it means final velocity is going to be 0 at the highest point. I think I should solve this. If it goes vertically upwards, final velocity at the highest point is 0 before it starts returning back. So they want us to know how high does the ball go. At the maximum height, velocity becomes 0. So because they want us to know how high, I will use V squared equals to U squared plus 2AS. So 0 squared equals to 18 squared. Now because it's going upwards, acceleration is going to be negative. Acceleration is going to be negative of G, which is negative 9.81. So this will be minus 2 times 9.81. The minus is because the acceleration is negative. So the plus becomes the minus because it is going to be plus 2 times negative 9.81, then times S. So this means S is going to be 18 squared divided by 2 times 9.81. 18 squared divided by 2 times 9.81. So S is going to be 16.5 meters. That is how high. Then how long is it before it returns to the cricketer's hands? So if it goes and comes back, it is going to travel the same distance upwards and the same distance downwards. So you are free to get the time from the hands to the maximum height and multiply it by 2. Or you are free to use S. You can use S equals to UT plus a half AT squared, where S will be 0 if it goes 16.5 and comes back 16.5, s will be 0 because s is a vector quantity. If it goes 16.5 and comes back 16.5, s will be 0. So I would say 0 equals to initial velocity is 18 times t. Because it goes and it comes back, the acceleration is still negative. So it is initial direction of motion is upward. So the acceleration is negative. So it will be minus a half times 9.81, then times t. So it means this is times t squared. So it means I'm just going to make t the subject. One t cancels. So I'll say 9.81 t squared is equal to 2 times 18 t. So 1 t cancels with the square. So I'll just divide to find t. 2 times 2 times 18 divide by 9.81. That is 3.7 seconds. Alternatively, I'm saying you can use v equals to u plus at. You find the time to reach the highest point. Remember, the highest point v is 0. Initial velocity is 18. The acceleration is negative because the body moved against gravity. The force is acting downwards. The motion is upward, so the acceleration is negative. Remember, we said if the force is in the opposite direction to motion, the acceleration is negative. We saw that in, I think we saw that in dynamics. So this is going to be negative 9.81 times t. So I find my value for t as 18 divided by 9.81. So t is 1.83. That is just to reach the highest point. So total time going and coming back is going to be twice t because it goes 1.83 seconds upwards, 1.83 seconds downwards. So the total is going to be 2 times that, which is still 3.7 seconds. So any formula can find that an airliner must reach a speed of 110 meters per second to take off. That means initial velocity is 0. U is going to be 0 and V should be 110. If the available length of the runway is 2.4 kilometers, so you have to change this times 1,000. This is 2,400 meters. And the aircraft accelerates uniformly from rest. Of course, I have already said initial velocity is 0. At one end, what minimum acceleration must be available if it is to take off? So you have to use v squared, I think, equals u squared plus 2as. We have v as 110. We have initial velocity as 0. We have the displacement as 2,400. You can check and see if that is correct by substitution. A rocket lifts off from rest, which means initial velocity is 0 with an acceleration of 20 meters per second squared. So that is a. Calculate its velocity. So we want to find v in a time of that. So you have acceleration, you know initial velocity, you know the time. So you can use v equals to u plus at because you know the v. You want to find v. Initial velocity is 0. Acceleration is 20. The time is 50. So you only want to find v. So that is just going to be 20 times 50, which is 1,000. Okay. I always don't solve these questions. I leave them for my students to solve. A speeding motorist passes a traffic police officer on a stationary motorcycle. The police officer immediately gives chase. His uniform acceleration is 40 meters per second, and by the time he draws level with the motorist, He is traveling at 30 meters per second. How long does it take for the police officer to catch the car? If the car continues to travel at a steady speed during the chase, what is this? What is that speed? Okay, so we shall first consider the police officer because this is going to be the acceleration of the police officer, 4 meters per second square. This is the final velocity because he was initially stationary. Initial velocity is 0. So let's first find the time. So I think I will use V equals to U plus AT. Because I have final velocity, I know the initial velocity, then I can find the time. So the time is going to be the final velocity, which is 30, divided by U is 0, so I'll just divide by the acceleration, which is 4. And I think 30 divided by 4 is 7.5 seconds. So the answer here is correct. Then how long does it take for the police officer to catch the car? That is 7.5 seconds. If the car continues to travel at a steady speed, that means the speed of the car has not changed. But note that at the start, when t is 0, the officer is starting from initial velocity 0, but at t equals to 0, the motorist is already having a speed which we want to find. And he remains with the same speed until the police officer levels with him or draws level. So the time is going to be the same for them. They will have traveled this for the same time by the time the police officer levels with him, and they will have covered the same distance. So if at t equals to 0, the motorist is just passing the police officer, and the police officer is also now just starting the motorcycle. Then after t equals to 7.5, they have now leveled because this one's speed was u, but this one was 0, and we want to find the u because after 7.5 seconds, the speed of the motorist is still u, but for the police officer it was now 30, and they are now level. They have covered the same distance in the same time. 7.5. So we want to find uh, the distance, the speed of the motorist. So because the motorist's speed is constant, it means the acceleration is going to be 0. So if I use S equals to ut plus a half at squared. For the motorist, because it's moving at a constant speed, the acceleration is going to be 0. This part will be 0. So all I need is to find S. So using V squared equals to U squared plus 2AS. I'm using the police officer now to find S. So S is going to be equal to 30 squared because that was the final velocity for the police officer, minus initial velocity for the police officer, which was 0 squared, then divide by 2 times A, divide by 2 times 4. So 30 squared divided by 8. 30 squared divided by 8. So S is 112.5 meters. That is S. So now I want to find, but S is equal to UT, so I will say 112.5 should be equal to initial velocity of the motorist, which is U. The time is the same because time is a scalar, 7.5. So the time for the motorist to cover a distance of 112.5 is the same time for the police officer to cover the same distance, because the police officer takes 7.5 to level and he has covered a distance 112.5. That means in that time of 7.5, even the motorist has covered the same distance. So making you the subject, I will just divide 112.5 divided by 7.5, which gives me u as 15 meters per second. So this answer is correct. I think that is the only tricky question here. A cricket ball is thrown vertically upwards with a speed of 15. What is the velocity when it first passes through a point 80 meters above the cricketer's hands? A cricket ball is thrown vertically upwards with a speed of 15 meters per second. What is its velocity when it first passes through a point 80 meters above the cricketer's hand? So the axis, it is moving upwards. The acceleration is going to be negative g, negative 9.81. So we want the displacement is this is 8 meters. That is the displacement. Initial velocity u is 15. So we want the velocity at 8. So I will simply use v squared equals to u squared plus 2as. So v squared is equal to u squared, which is 15 squared minus, because it's moving against gravity, 2 times 9.81. Then I multiply this by s, which is 8. So 15 squared minus 2 times 9.81 times 8. Then I find the square root. So this answer is correct. Of course, the motion is upwards. A car is initially stationary. It has a constant acceleration of 2 meters per second. Calculate the velocity of the car after 10 seconds. So the acceleration is constant. Initially stationary means initial velocity is 0. So you just use v squared equals to u squared plus 2as. Because we want final velocity, initial velocity is 0. We don't know s, so I will not use that equation. I have to look for an equation which has t. For example, I have v equals to u plus at. V equals to u plus at. I want v, I have the initial velocity as 0, the acceleration is 2, the time is 10. I think that one is direct. Calculate the distance traveled by the car at the end of 10 seconds. So if I already have v, then I can use either v squared equals to u squared plus 2as, because I have v, u, and I have a. Or I can use s equals to ut plus a half at squared, because I have the initial velocity as 0, I know the time, I know the acceleration. So any of those two equations can work. Calculate the time taken by the car to reach the velocity of 24 meters per second. So we want time this time. The acceleration has not changed. The initial velocity has not changed. So you can use v squared, or you can use v equals to u plus at. V is 24. Initial velocity is 0. The acceleration is 2. So you can find t. The car in the figure below is traveling along a straight road 80 meters per second. It accelerates at 1.0 meters per second for a distance of 18 meters. So this is s, this is the acceleration, this is traveling along a straight road at 8 meters per second. How fast is it then traveling? So this is going to be initial velocity. So we want how fast. That is now going to be the final velocity. So here I think we will use v squared equals to u squared plus 2as, because you want final velocity. Initial velocity is 8, acceleration is 1, displacement is 18. So I think that should give you the answer. A train traveling at 20 meters per second accelerates at 0.5 meters per second squared for 30 seconds. Calculate the distance traveled by the train. So we have this is going to be the initial velocity, acceleration, and this is t. Calculate the distance traveled by the train in this time. So we want distance, we need an equation which has distance. So I can use v squared equals, we don't know v final velocity, so I'll use s equals to ut plus a half at squared, because I know the initial velocity, I know the time, I know the acceleration. A train accelerates steadily from 4 meters per second to 20 meters per second in 100 seconds. So the time is 100 seconds. calculate the acceleration of the train. So this is initial velocity, final velocity, acceleration. So we want, sorry, this is time. So acceleration is equal to final velocity minus initial velocity over t. I think that one is direct. From its initial and final velocities, calculate the average velocity of the train. So from the initial and final velocity, calculate the average. Of course, if the acceleration is constant, this is a straight line, so the average velocity is going to simply be v plus u divided by 2. Then calculate the distance traveled by the train in this time of 100 seconds. So you can use s equals to ut plus a half at squared, because you know the initial velocity, you know the time, you know the acceleration, and you know the time. So you just substitute in that equation and you find, and you should be able to find the distance from that equation. Now someone will say, why are we using these equations for distance, yet we're talking about displacement s? As long as the direction has not changed, the displacement and distance are going to be the same, because we said these equations apply when the motion is in a straight line. So we don't expect that the distance is changing, or the direction is changing. As long as the direction is not changing, the displacement and distance are going to be the same in magnitude. So the equations can still apply. And every time we use them, we are assuming that the motion is uniform. Okay. The cyclist in the figure below is traveling 15 meters per second. Sorry, I have to move back. The cyclist in the figure below is traveling 15 meters per second. She brakes so this is initial velocity. When she brakes, it means the final velocity is going to be 0, because when you apply the brakes, it means you are coming to rest, so that she doesn't collide with the wall. Calculate the magnitude of her deceleration. So of course, her deceleration, acceleration is going to be final velocity minus initial velocity divided by t. So we don't have the time, or they gave us the distance between the brakes and the wall. So we don't have the time. I will not use this equation. So let me check. V squared equals to u squared plus 2as. So final velocity should be 0. Initial velocity is 15 squared plus 2 times the acceleration. Of course, I expect this acceleration to be negative because it is a deceleration. So then times 18. So the acceleration is going to be 15 squared divided by 2 times 18, which would give us 15 squared divided by 2 times 18, which gives us negative. This is a negative because when you take this to the other side, it's a negative. So negative 6.25 meters per second squared. The negative just confirms that it is actually deceleration. A car is moving at 80 meters per second. So this is initial velocity. Maybe the driver makes it accelerate at 1 meter per second. So this is acceleration. A distance of 18 meters. So this is s. What is the final velocity of the car? So we have acceleration, initial velocity, and s. So I can use v squared equals to u squared plus 2as. We want to find v. Remember to find the square root. So v squared equals to u squared, which is 8, plus 2 times 1 times s, which is 18. You should be able to get that answer. A cheetah starts from rest, which means initial velocity is equal to 0, and accelerates at 2 meters per second squared. That is the acceleration due east for 10 seconds. So this is t. Calculate the cheetah's final velocity. So I can use v equals to u plus at. The distance that the cheetah covers in this 10 seconds. So if since you have the final velocity, you can either use v squared equals to u squared plus 2as to find the distance, or you can use s equals to ut plus a half at squared to find the distance because everything is now known. An athlete accelerates out of her blocks. That means initial velocity is 0 out of her blocks. At 5 meters per second, the acceleration is 5 meters per second. How long does it take for her to run the first 10 meters? So this is s. We have initial velocity is known, acceleration is known, and s is known. And the question is how long? That is time. So we want to find time. So here we shall use s equals to ut plus a half at squared, where u will be 0, s is 10. So I'll say 10 is equal to a half times 5 times t squared. So this gives you t as 2 times 10 divided by 5, which is 2. Which is 2 times 10 divided by 5, which is 4. Then square root t squared is equal to 4. Then you get the square root, which gives us 2. What is her velocity at this point? So if you want her velocity, you can use v squared equals to u squared plus 2as. U squared is 0, so we say v squared equals to 2 times 5 times s, which is 10. Then you find the square root. So we have 10 times 10, then under the square root, which gives us 10. And lastly, I think this should be the last example. A bicycle's brakes can produce a deceleration of 2.5 meters per second squared. How far will the bicycle travel before stopping? That means final velocity is going to be 0. This is the acceleration. Because it's a deceleration to be a negative, in the calculation to be a negative. If it is moving at 10 meters per second, so this is going to be the initial velocity. Because it's decelerating, the final velocity is 0 when the brakes are applied. So how far? We are finding s. So I can use v squared equals to u squared plus 2as. Final is 0 squared. Initial is 10 squared plus, because it's the deceleration, I'll put a minus. So this will be plus negative. So this becomes minus 2 times 2.5, then times s. So I just make s the subject. So this means s is going to be 10 squared divided by 5. That is 2 times 2.5. I think it's 5. So that means s is going to be 100 divided by 5, which is 20 meters. Okay, so I think I've tried my level best to give hints of these solved past paper questions. Like I said in my class, I don't solve them. It's always students who solve these questions for practice, and then they become very confident with using equations of linear motion. Okay, let's talk about free fall acceleration. Let's understand free fall acceleration, or acceleration of free fall, or acceleration due to gravity, or which we shall scientifically call gravitational field strength in a unit called gravitation. That will be in paper 4. So a very common example of uniformly accelerated motion is when a body falls freely near the Earth's surface. When a body falls freely near the Earth's surface is a very good example of free fall. So because of the gravitational attraction of the Earth, all objects fall with the same uniform acceleration. This acceleration is called the acceleration of free fall and is going to be represented by the letter g many times. A very common example of uniformly accelerated motion is when a body falls freely, especially near the Earth's surface, or it can be near any other planet. And this is normally because of the gravitational attraction of the Earth or the gravitational attraction of the other planet. And we are saying all objects fall with the same uniform acceleration if they are very close to the Earth's surface. And this is what we call the acceleration of free fall. We normally use the letter g to represent acceleration of free fall, and close to the Earth's surface is about 9.81 meters per second squared. Its value is given to be 9.81 meters per second squared, and it is always directed towards the Earth's surface or towards the center of the Earth. That means if the object moves against the gravitational attraction of the Earth, then the value of g is going to be negative. That's why you must have seen that in calculations I've always been using negative for g if the motion was initially upwards. So what we mean by free fall motion is a motion with no acceleration other than that provided by gravity. The body has no any other acceleration apart from that provided by gravity. So we say it is falling freely under the only influence of gravity. So free fall is motion with no acceleration other than that provided by gravity, or other than that provided by the gravitational pull, or other than that provided by the gravitational attraction of a planet or of another large mass. So the acceleration, this acceleration is going to be called the acceleration of free fall. The acceleration of a body falling due to gravity is going to be called the acceleration of free fall, and we shall always use the letter G to represent it. This value here is about 9.81 meters per second squared directed towards the Earth. This is on the Earth. It is not the same value on the Moon, because on the Moon it is a 60th of this, which is approximately 1.6. But close to the Earth it is about 9.81 meters per second squared. And it is always directed downwards after acceleration is a vector quantity. And the gravitational pull of the Earth is towards the center of the Earth. So we assume that when we are standing on the Earth, then it is pulling us downwards towards its center. So the acceleration is always directed towards the center, its center. So the fall must be in the absence of air resistance. So this acceleration remains uniform if air resistance is negligible. But of course, in most situations, this can be just assumed to be true. Although we cannot assume that air resistance is always absent every time an object is falling. So this statement of 9.81 meters per second means that the speed of a free-falling body increases by 9.81 meters per second every second. If a body is falling, its speed increases by 9.81 meters per second every second, which means that when a body is thrown vertically upwards, the opposite happens. Its speed decreases. When the body is thrown vertically upwards, its speed decreases by 9.81 meters per second every second, assuming that air resistance has been neglected. So we should note this very, very carefully, that the acceleration of free fall causes the speed of a body to increase when it is falling downwards, and the acceleration of free fall will cause the speed of the object to decrease when the object moves against the force due to gravity. So although the acceleration due to gravity is considered constant close to the Earth's surface, of course it tends to vary slightly over the Earth, since the Earth is not a perfect sphere. Even though we assumed it is approximately 9.81 on the Earth's surface, it is actually not really the same value on every parts of the Earth, because the radius of the Earth from the center to the equator is not the same as the radius of the Earth from the center to the poles. In fact, the equatorial radius is much bigger than, or is bigger than, the polar radius, which means the value of acceleration of free fall on the equator is not exactly the same as the value of the acceleration of free fall at the poles, but on average, it is approximately 9.81. So we shall see that difference in A level. That will be a unit called gravitation in paper 4. Okay, so that is acceleration of free fall. Here I have a thought-provoking question for you. This is really thought-provoking. So my thought-provoking question is here, Does a more massive object accelerate at a greater rate than a less massive object? In other words, would an elephant free fall faster than a mouse? Of course, we know that an elephant is more massive than a mouse. Does it mean when they are released from the same point that an elephant will fall faster or will free fall faster than a mouse? Of course, a layman will immediately think, yes, an elephant is bigger. But what is causing the free fall is the acceleration due to gravity. There is no any other acceleration apart from that caused by gravity. And the acceleration due to gravity is not depending or is not going to depend on the masses of either the elephant or the mouse. It actually depends on the mass of the earth, not the mass of these objects above the earth's surface, but the mass of the object which is creating the gravitational field or the gravitational pull. So a layman would think it is the elephant, but if there is no air resistance, if there is no air resistance, these two objects would arrive at the same time. So the answer to this is absolutely not. In the absence of air resistance, all bodies would free fall with the same constant acceleration because the acceleration will not depend on their masses. The acceleration is independent of their masses. So acceleration is independent of their masses. So all bodies would fall with the same acceleration because the acceleration is independent of their masses. However, if there is air resistance, maybe then that would be that's where there will be a problem. More massive objects will fall faster if there is an appreciable air resistance because the air resistance will overcome or will make the terminal velocity of the mouse to be very small. So it will accelerate, or it will move at a lower speed than the elephant. But if there is no air resistance, all bodies will fall with the same constant acceleration because the acceleration is independent. The acceleration is independent of, of the masses of these objects. So just to give you a few more examples of free-falling objects, you can think about a spacecraft in space with its rockets off. If the rockets are turned off and a spacecraft is in space, in a continuous orbit or going up for some minutes and then down, that is an example of a free fall. The moon's orbit around the Earth is also considered to be an example of free fall. Examples of objects not in free fall could include if you are standing on the ground. If you're standing on the ground, you can't consider yourself free fall because the gravitational acceleration is counteracted by the normal reaction force from the ground. So when you're standing on the ground, you can't expect yourself to be under free fall because you're exerting a gravitation, your weight is acting towards the center of the earth, but the normal reaction from you is also acting on the earth in the opposite direction, and these are being cancelled out. If you're moving horizontal or flying horizontal in the air, or in the airplane, it's not an example of free fall because the wings lift is also providing an acceleration. So you should be able to know the difference between acceleration of free fall and then other forms of acceleration. For acceleration of free fall, the only force acting on the object is the force due to gravity. That is what we mean by free fall because the acceleration is only the acceleration caused by the gravitational pull of the earth in that case. So we have concluded that a more massive object and a less massive object will all fall at the same time, or they will all arrive at the same time. And I said a layman would think that heavier objects fall faster than lighter ones. But this idea is a consequence of the effect of air resistance on light objects with a large surface area, such as feathers. However, Galileo Galilei suggests that in the absence of air resistance, all bodies would fall with the same constant acceleration because the acceleration is independent of these bodies' masses as long as there is no air resistance. In his experiment, Galileo verified that in the absence of air, for a body starting from rest, it means at initial velocity being equal to 0. If all bodies start at rest, it means the initial velocity for all bodies is 0 in the absence of air resistance. And the distance is proportional to the time squared. So if we use S equals to U plus AT squared, if all body S is equal to UT plus a half AT squared, if all bodies start from rest, initial velocity is 0. It means this part will be 0 and S will be equal to a half AT squared. If all bodies start from rest, the distance S is directly proportional to T squared. In that case, therefore, if we are considering a free fall, all objects fall at a constant rate, since free fall is the motion of objects under the sole influence of gravity, under the only influence of gravity. So free falling objects are not expected to encounter air resistance. Therefore, we conclude that a more massive object and a less massive object are expected to arrive or to fall at the same rate. That is according to Galileo's experiment. He verified that in the absence of air resistance, for a body starting from rest, or for bodies starting from rest, the distance is only proportional to the time squared. The distance is not going to be, the distance is proportional to the time squared, and the acceleration was a constant value for all bodies. The acceleration was independent. The acceleration was independent of the masses of these bodies. So whether you are throwing a feather and a coin, as long as you are throwing them or releasing them from the same point where initial velocity is equal to 0, you are releasing them from the same point, initial velocity is equal to 0, and in a vacuum where there is no air resistance, we expect them to fall at the same rate. So the acceleration is going to be constant. And if the acceleration is constant, that means if it is 9.81 that is close to the Earth's surface, it means that after 1 second, each will have the same speed and will have covered the same distance. After 2 seconds, both of them will have doubled their speeds and will have doubled their distances. And therefore, they would arrive on the ground at the same time. So, more massive objects will only fall faster if there is an appreciable amount of air resistance. If there is no appreciable amount of air resistance, they will fall at the same rate because the acceleration is independent of their masses. That is according to Galileo Galilei. Okay, so let's understand free fall in more details. So to understand the free fall, we are going to consider a falling object. Let us assume a dog is falling off a plane as illustrated by this diagram here. So to start with, the dog is going to be falling slowly. It has not had time for its speed to increase. So it means its initial speed is 0. So here we are saying the initial speed of the dog is 0 at t equals to 0. So the only force which is acting is the air resistance. The only force which is acting is not air resistance, is the weight. So the only force which is acting is the weight of the body. So the force due to air resistance is negligible, is 0 at t equals to 0 because it's just falling. Of course, the resistive force also depends on speed. If you have been in a car, you must have noticed that as the car speeds up, you feel more wind blowing because the resistive force also depends on the speed of the moving object. So here it means the resultant force, F, which would be equal to the mass times the acceleration, would simply be equal to the weight. But remember, the weight is mg. So we would simply say the ma would simply be equal to mg. So the acceleration is simply g at the start of the motion. So there is really only one force acting on the dog, and that is the force due to gravity, or the force of gravity. The dog is going to fall faster, in other words, accelerates due to this force, because it's initially the only force which is acting on the dog. That is at t equals to 0, when the motion has just started. So in that case, if the motion has just started, then we would say the resultant force acting on the dog, which I'm going to call Fr, R is standing for resultant. So the resultant force acting on the dog is going to be the weight. And the weight is given by mg. So at t equals to 0, when the dog will just starts moving or falling off the plane at t equals to 0, the acceleration is equal to g, which is going to be 9.81. Let's see what happens when the dog has fallen for some time. Of course, as it starts falling, because there's an acceleration, the speed increases. So what does that mean? The force due to air resistance now starts increasing. And remember, the resultant force is the difference between the weight downwards minus the force due to air resistance. So because the force due to air resistance is now increasing, it means the difference is becoming smaller, so the resultant force is decreasing. So in that case, therefore, we say that the resultant force Fr is going to be the weight downwards minus the air resistance. So the mass, the resultant force is given by ma according to Newton's second law. So this would be called the weight minus the force due to air resistance. So if I divide both sides by a, I have that a is going to be equal to g minus F due to air resistance divided by m. So it means acceleration is less than g, because to find the acceleration I get g minus something. So it means as air resistance, as the object continues moving, the air resistance increases. So with time, the acceleration decreases. So the acceleration is decreasing. But is not, the speed is not, has not started decreasing, not at all. The speed is not decreasing, it is the acceleration which is decreasing, which means the rate of increase of velocity is becoming smaller. Okay, then there would be a point where when you look at this R and this one, it appears as if the force due to air resistance upwards is balancing with the weight. What is the difference between these two? It means the resultant force here is going to be 0. And if the resultant force is 0, it means the acceleration is no longer going to be equal to g or less than g, but simply to be 0. So we say that the acceleration has decreased from g to 0. And when the acceleration is 0, for a body which was initially moving, we say that the velocity has remained constant. And that velocity is what we call terminal velocity in dynamics. So uh, the resultant force Fr is going to be the weight minus the force due to air resistance. But remember, at this point, with the time, the air resistance is equal to the weight, which means the difference between the two is 0. So the resultant force is going to be 0, which makes the acceleration to be 0, and therefore the velocity is constant. That constant velocity is what we call terminal velocity. Remember, from dynamics, we say the force due to air resistance is directly proportional to the square of the speed for large values of v. So as speed increases for a falling body because it has acceleration, the force due to air resistance also increases. A point reaches when the speed can't increase any further because the force due to air resistance has balanced with the weight. In that case, the resultant force is 0. It means the acceleration is 0, the speed must remain constant. And that constant speed is what we call the terminal velocity in dynamics. Okay, so here is a simple illustration of terminal velocity. I mean, free fall, say in a fluid such as a liquid or a gas. Initially, the only force we had was force due to gravity, but then as time goes on, the force due to air resistance increases because the speed of the object was increasing. Then it reaches a point where you see that the speed is not increasing any further. So as the speed of the ball increases, the force due to air resistance also increases. then until a point when the force due to gravity balances with the force due to air resistance, and at this moment, the force upwards is the same as the force downwards, and the speed becomes constant, and the object is described as having what we call terminal velocity. So maybe I can repeat this. Initially, we only have force due to gravity, so acceleration is equal to g. Initially, there's an acceleration. The speed starts increasing. When the speed of the ball increases, the air resistance also now starts increasing in the opposite direction. So it means the resultant decreases, it decreases, it decreases, it decreases until a point when the resultant becomes zero because the force due to gravity is equal to the force due to air resistance. So they cancel out each other. At this point, the resultant force is zero, the acceleration becomes zero, so it means the speed becomes constant, and the object is said to be describing what we are calling terminal velocity. So that is what we mean by a terminal velocity. Okay, activity. So this activity, you can do it in your class, or your teacher can help you to do this activity. But you don't, A-level students do not need a teacher to do anything. I don't think they need a teacher to do anything. In a pair, estimate the acceleration due to gravity. You're going to use what I call a rough method. So you'll go to the top of your college building. You should be in a pair, of course, because one is going to drop the object, another one is going to press the start and stop the stopwatch for simplicity. You need to check the distance between the top floor and the ground. It can be measured using a tape measure. You can measure it using a tape measure. You need the time taken by the object to fall from top floor to the ground floor. And of course, you are going to ignore the air resistance. You can use a metallic object for better results maybe. It can be determined using a stopwatch. So you need a time using a stopwatch, you need a distance using a tape measure. So if you assume that air resistance is negligible, and you are going to assume that you are going to drop the object, that means the initial velocity is going to be zero. So using S is equal to ut plus a half at squared, you notice that S is going to be equal to a half gt squared, where A is equal to g, because we are trying to find the acceleration of free fall close to the Earth's surface. So if the body falls from rest, then g is equal to, making g the subject, g is going to be 2s over t squared. You can repeat this for the same object and get the average value of g, because it is always going to be necessary for us to get an average value for any measurement. However, this is just a rough method. The best method would be being able to change S and obtain different values of t, so that now you plot a graph. That would have been the best method. Being able to change S and obtain different values of t, and then you investigate a graph of, say, S against t squared and see how the graph looks like. That would be the best method. But for this rough method, you can just calculate g from g equals to 2s over t squared, where s is the distance from the ground to the top floor where you have dropped the object, and t is the time you have recorded for the object to fall through that distance. You can try to repeat a measurement, you can try to repeat the experiment for the same height and obtain an average value of g. Better methods for this could be, we could use an electronic timer to obtain a better value for t rather than using a stopwatch. An electronic timer would be a better candidate to obtain a better value of g. So this is going to be an easier method. So there are easier methods for finding g which can be used in the laboratory. And I want us to explore one. One of them is this one, using an electronic timer and a trap door, which could be. So using an electronic timer, we are going to find the time this object falls from the electromagnet to the trap door. So the electronic timer will tell that time. As soon as the object leaves the electromagnet, the timer starts. and as soon as the object reaches the trapdoor, the timer stops. So we shall get a perfect value of t. Then using a meter ruler or a tape measure, we can measure h. Then we can adjust the value of h because we are interested in plotting a graph so that we get a better results from the graph. So that is using an electronic timer. So a steel ball is held by an electromagnet. Why an electromagnet? It is really very hard for you to release an object without adding an extra force. So if the ball is metallic, then an electromagnet is the best option for releasing the object because the electromagnet will cease to be a magnet when the current stops flowing. It's just press a switch and the current stops flowing and it loses its magnetism, especially if it is made out of soft iron. Because soft iron is soft iron immediately becomes a magnet and almost immediately loses its magnetism when the current stops flowing. So an electromagnet is the best device for releasing metallic objects because it is really very hard for us to release an object on our own without adding any extra force on the object. So when the current to the magnet is switched off, the ball begins to fall and an electronic timer starts automatically. The ball falls through a trapdoor and this breaks a circuit to stop the timer. So the timer is designed so that when the ball hits the trapdoor, the circuit is intercepted and the timer stops. This tells us the time taken for the ball to fall from rest through the distance h between the bottom of the ball and the trapdoor. So that will give us the time of fall in that case. So let's see the analysis of results. So to analyze the results, of course, we shall use equations of motion. S is equal to ut plus a half at squared. We have assumed that air resistance is negligible, so the acceleration is constant. So if S is equal to the vertical distance h, then the acceleration is equal to g. So S is going to be a half at. If we release the object from rest, that means the initial velocity was 0. So this could give you a value of g, but this is not going to be satisfactory. So a more satisfactory method would be to adjust h. So a more satisfactory procedure is to take measurements of t for several different values of h. So we adjust h and we repeat the experiment and obtain different values of t. And if we have several values of h in maybe centimeters and several values of t in maybe seconds, of course, what we shall need the values of t squared so that we plot a graph. So therefore we can deduce g from the gradient of the graph of h against t. So if I plot h against t squared, is going to be a straight line through the origin. H in maybe centimeters against t squared in seconds squared. So this is going to be a straight line through the origin. And from this equation here, h equals to a half gt squared. If I compare with the y equals to mx plus c, there is no y-intercept. So the gradient is going to be a half of g. So the gradient is going to be a half of g because the graph is going to be a straight line through the origin. So the gradient is going to be a half of g. So gradient equals to a half of g. If I plot h against t squared, you can also plot logarithm, but this is the easiest. So it means the value of g is going to be twice the gradient. And this will be a better method than just pressing the calculator to use one value of h and one value of t to find g. So this would be a better method for obtaining or measuring the acceleration due to gravity. Adjust h and obtain different values of t and then plot a graph. The other simpler method would be using light gates. We have already seen how light gates are used. So let's say we have one light gate, say here, and another light gate here. And we are still going to use an electromagnet to drop a sphere The only thing we need to do is to measure the distance between the light gates. Let's say that is h. And of course, the light gates are connected to a timer. These ones are joined to a timer. They are connected to a timer, an automatic timer. So measuring the distance between the light gates, that is h, and recording the value of t from the timer. So it is almost the same as the first example. So we shall still measure the distance between the light gates. So a steel ball is held on an electromagnet, and when the electromagnet is switched off, the ball interrupts or it intercepts the light gates or the light, and a timer is started. As the ball falls, it interrupts the second beam of light, and the timer stops. So it is an automatic timer. So we just measure the vertical distance h between the two light gates using maybe a ruler or a tape measure. Then we vary or we adjust the distance h between the two light gates. And again, we are going to plot a graph of h against t squared. Of course, to be a straight line as before. And from h equals to a half gt squared. If we compare this with y equals to mx, maybe plus c, there is no y-intercept. So we notice that the gradient is equal to g divided by 2. So g is going to be twice the gradient. So that is how we determine the acceleration of free fall close to the Earth's surface. The most important thing is to make sure that the time measured or the time recorded is as accurate as possible, because using a stopwatch cannot give us a very good value of t, a very certain value of or a very good value of time because of reaction time of a human being. And also using an electromagnet minimizes the problem of adding a force on the electromagnet. But of course, still, even if we use an electromagnet, there is still a challenge, because sometimes the electromagnet may still retain some magnetism which may delay the fall of the object. And also the tape measure or the meter ruler we are using to measure the value of height h only gives us values to about 1 millimeter, because the meter ruler measures to 1 decimal place in centimeters. So that is about 1 millimeter. So it means the value of h may not also be as accurate as possible. There could also be a random error in the value of h and so on and so forth. So those could affect the results. But still, we're just looking for an average value or an approximate value of g. Okay, so some sources of uncertainty in the methods we have just talked about. The electromagnet may retain some magnetism sometimes, even if it is soft iron. So when it is switched off, and this may tend to slow the ball's fall. So if the electromagnet retains some magnetism, the steel ball may take a short time before it starts falling. So consequently, the time recorded by the timer may be longer than if the ball were to fall completely freely. That's one limitation. Number two, measuring the height h is also an awkward procedure. You can probably only find the value of h to within plus or minus 1 millimeter at best, because if you use a tape measure or a meter ruler, it measures to 1 decimal place in centimeters. That is approximately 1 millimeter is the uncertainty. So there is a random error in the value of h. There would be a random error in the value of h in most cases. We can also use, I think we talked about a ticker tape timer. We could also use a ticker tape timer to measure or to determine g. So we could use a ticker tape using a ticker timer. For example, we attach a weight onto the tape, and then we just release the weight so that as it falls, dots are made onto the tape, and our task is just to analyze the dots. So as it falls, it pulls the tape through a ticker timer. The spacing of the dots on the tape is expected to increase steadily, increase uniformly, showing that the weight is accelerating, because an increase in the distance between the dots, as we saw in lesson 1, indicates that the speed is increasing, which means the tape the mass is accelerating. So by analyzing the tape, we can find the acceleration, but of course here there is also a limitation. There could be friction. The main problem arises from friction between the tape and the ticker timer. So there could be friction between the tape and the ticker timer, which affects the free movement of the weight. But this could also give us the acceleration due to gravity of a falling mass using a ticker tape timer. By analyzing the tape, we can find the acceleration, because remember these dots are made at equal time intervals of about 0.02 seconds. So I can tell by looking at the dots, I can find the rate at which the speed is increasing by looking at the distance between the dots, because um, the spacing of the dots on the tape is going to increase uniformly, which would mean the acceleration is going to be uniform in that case. Okay, so how do we represent free fall by graphs? And this is the most important part. Representing free falling objects by graphs. So let's consider a simple illustration where an object is going to fall from the top of a building. Since it is falling, if it is falling downwards, we shall say the initial direction of motion is positive. The initial direction of motion in every kind of motion is always considered to be positive. So it is falling freely. In the absence of air resistance, initial velocity is zero. In the absence of air resistance, we can assume that the acceleration is positive. If the reference point is, or the observation point is the ground, so it means if I sketch a position time graph, by the time the object reaches the ground, the position should be zero. And if the object is at a certain height h with the reference the ground, the position here is going to be the highest. So if I sketch a position time graph, it should look like that. Initial, it is almost horizontal, to mean that the initial velocity is zero. After the position time graph, the gradient is always going to be the velocity. So a horizontal line means the gradient is zero, which means initial velocity is zero. But finally, with the time, we notice that the gradient is increasing, which means velocity is actually increasing because there is an acceleration, which is the acceleration due to gravity. So the line now becomes steeper as the position decreases, or as it moves towards the ground, because the reference point is the ground. So at a zero position, that is the ground. So as it falls towards the ground, the line is becoming steeper, or the curve is becoming steeper. So the slope of any position time graph is going to be the velocity. When I talk about the slope, that is the gradient. A curved line on a position versus time graph signifies accelerated motion. So this is an acceleration. If it was a straight line, it would mean there was no acceleration, because the gradient would be constant, which would mean that the velocity is constant. The small initial slope indicates a small initial velocity. That is, here we have a small initial velocity. And the large final slope, this is a big slope, indicates that there is a large final velocity. So if it was initially horizontal, it means initial velocity is zero, but then it starts curving, which means the gradient is increasing. And here it is very steep, which means the gradient has increased to a maximum value. Remember, the gradient or the slope is the velocity in this case. So that would be the graph for a position time graph for a body which is just falling free. Number two, how would the velocity time graph look like? Remember, it is starting from rest, is a free fall, so initial velocity is zero. So the graph must start from the origin. For a velocity time graph, this must start from the origin. So if there is no air, the acceleration is constant. How do you show that the acceleration is constant? It means if there's no air resistance, the acceleration is constant. So this should be a straight line, because the gradient of a straight line is constant, which would mean the acceleration is constant, since a velocity time graph gives us acceleration. So the graph for a velocity time graph, sorry, I would start with the displacement time graph anyway. So the displacement time graph, because displacement is a vector quantity, where we start from is the initial direction of motion. So if we start from the top, it means at the top here, the initial displacement is 0. So when we move towards the ground, when we reach the ground, the final displacement will be maximum. And if there is no air resistance, the displacement increases uniformly. That's why we have a curve like this one here. The displacement is going to increase smoothly like this. So that if I try to find the gradient is increasing because the acceleration, there's an acceleration which is g, the velocity is increasing as the object falls. How do I show increasing velocity from a displacement time graph? I must draw a curve of increasing gradient. That's why you see this curve has this smooth curve has an increasing gradient. This is if there is no air resistance. It must be a smooth curve because if there is no air resistance, the acceleration must be equal to a constant, which means the velocity must increase uniformly. So if I try to find the tangents to this curve in equal time intervals, the tangents will be increasing uniformly. So this smooth curve shows increasing velocity because when an object is falling downwards, the velocity increases. However, if there is air resistance, we have seen the dog falling from the plane. Initially, when u equals to 0, the force due to air resistance is 0. So it means the acceleration was simply g. But with the time, as air resistance increases, the acceleration tends to 0. In other words, the velocity becomes constant. And how would we show constant velocity using a displacement time graph? We must draw a straight line. That's why we initially start with a curve and then it becomes a straight line. Initially, the velocity increases because the gradient is increasing and then it becomes a straight line, which indicates that initially there's an acceleration initially, so the velocity would be increasing, but with the time, when the force due to air resistance is equal to the weight of the object, the velocity remains constant because at that point the resultant force is equal to 0. So here with air resistance, when we have a straight line, the force due to air resistance is equal to the weight of the object. The force due to air resistance levels out with the weight of the object, which means the acceleration is going to be 0 because the resultant force is going to be 0. And at that point, the velocity becomes constant. Because velocity is the gradient, we must have a straight line. It is constant and not 0. That's why the line is not horizontal. So the velocity is constant but not 0. That's why the line is not horizontal. Okay. So in the absence of air resistance, the graph continues to curve as the object accelerates. The gradient becomes steeper to show that the velocity increases. In the presence of air resistance, if there is air resistance, the graph later levels off. In other words, it becomes a straight line with a constant gradient as the object reaches what we call terminal velocity. So the displacement time graph would look like that. With a lot of practice, you'll master these curves. If you watch the solved past paper questions, you'll become very familiar with them. Okay, let's see what happens to the velocity time graph. So from the displacement time graph, we could deduce a velocity time graph. Initially, the object started from rest, so that means initial velocity should be 0. The graph starts from the origin. But there's an acceleration. If there's no air resistance, the acceleration remains constant in the absence of air resistance. So how do we show constant acceleration from a velocity time graph? It must be a straight line through the origin. So without air resistance, it is a straight line through the origin. But if there is air resistance, the force due to air resistance increases as the speed increases, which means the resultant force, which is given by the weight minus the force due to air resistance, the resultant force decreases. And remember, resultant force is mass times acceleration, so the acceleration decreases until a point when weight equals to the force due to air resistance, which means acceleration will be zero because the resultant force will be zero. And when the acceleration is zero, v becomes constant. How do we show constant velocity on a velocity time graph? That should be a horizontal line. So initially, I don't think this graph is very correct because there's air resistance, but the best way to draw this would be something like this. That would be the best way to draw this because there is air resistance. The velocity will not increase at the same rate for long. This is too much time. So the best way to draw this would be a line below the other one, and then it becomes horizontal. That would be the best way to draw that rather than drawing this. So with air resistance, so I'm taking this one as my correct graph. It should always be below the first one because the air resistance makes the maximum velocity to be less. So with air resistance, the acceleration goes on decreasing. Of course, the velocity will always be, the line will be always below the first one. And with the time, the line becomes horizontal because here the acceleration becomes zero when the velocity becomes constant. So in the absence of air resistance, the graph continues as a straight line, constant gradient, thus constant acceleration, because the gradient of a velocity time graph is the acceleration. In the presence of air resistance, the graph later levels off to terminal velocity. In other words, later on the graph will have zero gradient, indicating that later on there will be no acceleration. Okay. So how would the acceleration time graph look like? So for still motion where the body was falling downwards, we are still was under free fall. The acceleration time graph, if there is no air resistance, the acceleration is constant. So a graph of acceleration against time is a horizontal line. Because there is no air resistance, acceleration is equal to g. If there's no acceleration, there's no air resistance, acceleration is equal to a constant value g, which is 9.81. That is a horizontal line. But if there is air resistance, we have seen that the acceleration goes on decreasing. Because if there is air resistance, the resultant force F, which is mass times acceleration, is going to be the weight minus the force due to air resistance. And it means MA is equal to mg minus the force due to air resistance. So as the body moves, the air resistance increases. So this difference becomes smaller. And this means the acceleration also decreases. So it tends to zero. That's why the graph has a decreasing gradient. But remember, why is the gradient decreasing? Again, when the acceleration reduces, the speed decreases. And when the speed decreases, the force due to air resistance also decreases as the speed decreases. So the acceleration decreases and tends towards zero. So if the air resistance can't speed up any further, it means that the rate at which the velocity changes also becomes smaller. So this is going to be a graph with decreasing gradient. So the graph tends towards the zero. Okay. So in the absence of air resistance, the graph is horizontal line with a zero gradient and constant acceleration. But in the presence of air resistance, the graph curves down to zero as a resultant force becomes zero, indicating no acceleration or indicating that the acceleration decreases to zero. So acceleration decreases towards zero when the velocity becomes or tends to becoming constant. Okay. Now we have seen a body falling freely in air. Suppose the body then bounces. There's a possibility of a body bouncing, falling and then bouncing. So let's again consider a situation where a body is falling from a building but then it bounces. From the animation on the right hand side of this, or it is your left hand side, I don't know, you notice that when the body bounces, as it keeps bouncing, the vertical height to which it rises decreases. And if the vertical height to which it rises decreases, it means also its maximum velocity decreases. And therefore, its position is decreasing with relative to the ground. Its displacement is decreasing with relative to the ground. So it means its maximum velocity is also decreasing with relative to the ground. So it means in the absence of air resistance, here we shall just ignore air resistance. So V squared is equal to U squared plus 2AS. So if it is falling freely, initial velocity is 0. So it means V squared is going to be directly proportional to S. If 2 and A are constants. So because S decreases, the maximum velocity also decreases, or the final velocity also decreases. Therefore, if I am to sketch a graph, in that case, it is almost the same as the velocity time graph we have drawn, but I want you to notice that it bounces back. That means it always moves in the opposite direction. Since the acceleration is constant, as it bounces for every bounce, the lines will be parallel. So this one, this one, this one, and this one are parallel, which means they have the same gradient to indicate that the acceleration has remained constant if there's no air resistance. However, for the first, here it hits the ground and it bounces. Bouncing is represented by a vertical line. It hits the ground, it rebounds. When it rebounds, it moves in the opposite direction. That's why you see now the velocity is decreasing because it's moving upwards. Here it has reached the maximum height. Then now it starts moving downwards. It hits the ground again, it bounces. When it rebounds, again it moves upwards. It reaches the maximum height. Then, of course, at maximum height, always velocity is 0. Then it moves downwards. That's why velocity is increasing. Initial direction was downwards, so downwards the velocity is positive. Then it hits the ground the third time, it bounces. When it rebounds, again now the velocity decreases as it moves upwards. Then again it continues downwards. So because every time the line crosses the x-axis, it means there has been a change in direction. So this will be the graph for velocity against time for a body which is bouncing. And because the lines are parallel to each other, we say that the gradient is the same. So the acceleration is the same even when the body bounces. So the acceleration remains constant. It remains g, 9.81. So if I was to sketch a graph of acceleration against time, for this motion, it will still be the same, a horizontal line, because the acceleration has not changed. The straight lines, the parallel lines means that the gradient of each of the lines is the same. That means even when a body bounces, the acceleration remains constant. Because it was initially moving downwards, the acceleration is positive and is 9.81. If the initial motion was upwards, then this line would be below the x-axis. If the initial motion was upwards, the graph for acceleration against the displacement against time would be below the x-axis because it will be constant but in the negative direction. Okay. So the height of the motion is reducing after every bounce. So the maximum velocity also reduces. That's why you notice that the maximum velocity is not the same after every bounce, even at the bottom. So the maximum velocity reduces after every bounce because the maximum height reduces. When the line crosses the zero axis for a velocity time graph, velocity is 0 and velocity is 0 at maximum height. So here the body is at maximum height, at maximum height, at maximum height. We represent bounce with a vertical line. As an assignment, I would ask you to predict the displacement time graph for a body or for the above motion. Also predict the displacement time graph if the ball bounces to the same height, and the velocity time graph for this case. One of my students was able to predict this. You should also, this one here is of course the graph of position against time would almost look like this illustration here, or this would help you to predict the graph of position against time, but I want a displacement time graph for this kind of motion. A good student would take this backwards, would take the velocity time graph backwards, and I think this is what my student did. He drew the axis in this, where wherever the velocity was, wherever it was, he had a straight line, he drew a curve for displacement. Then there has been a change, a bounce. Then the velocity starts decreasing. So he was drawing something like this. Because to show decreasing velocity, you must draw a graph of decreasing gradient. Then velocity increases. Then you draw something like this. Then there's a bounce. Velocity decreases, you draw a curve of decreasing gradient. Then velocity increases, something like this. Then there's a bounce. Then velocity decreases, so something like that. So it drew a curve like this. So literally, this is what the student has, I think. Something like this. Then there's a vertical line, something like this. Then again another vertical line, something like that. And so on and so forth. So this will be the displacement against time graph, something like that. So you can try to think about it. Of course, you just move backwards. From the velocity time graph, you should be able to deduce a displacement time graph. I've given you a hint. If my students were able to do this, you should also be able to do that. So you can predict a displacement time graph if the ball bounces back. It bounces back but to different heights. Of course, the same height, it is very easy. You just draw the same graphs but reaching the same level. You should also be able to predict the velocity time graph if the body reaches the same height. Of course, it will be just a graph where these lines stop at the same level. That is an assignment for you to think about. Then how about if the object is launched upwards? Now, of course, if the object is launched upwards, it means remember the action is always downwards. So if motion is in the opposite direction to the direction of if motion is in the opposite direction to the acceleration or to the force, it means the acceleration is going to be negative. So if the object is projected upwards, it can't move with an initial velocity of 0. So it has an initial velocity which is not 0. Not 0. So this graph cannot start from the origin. But when it reaches the highest point, the final velocity is 0. So if there is no air resistance, then this is going to be a straight line. But this is a straight line of a decreasing gradient, of a decreasing velocity. So it must be projected with some velocity. But when it reaches the maximum height, velocity is 0. So here it has reached maximum height. Maximum height, where velocity becomes 0. Maximum height, velocity becomes 0. And when you look at this graph here, if I try to find the gradient of this line, it is a negative value. So the acceleration is negative. So a graph of velocity of acceleration against time is going to be below the x-axis. The acceleration is a negative value, or let's say negative g. If the object is projected upwards against gravity, the acceleration is negative. So if I sketch a graph of acceleration against time, it is below the x-axis, because the gradient of a line like this one, where the velocity is decreasing, is a negative gradient. When a body is projected upwards, it is moving against gravity, the acceleration is negative. The velocity decreases. At maximum height, the velocity is 0. Suppose the object reaches the maximum height and it falls back to the ground. Let's consider an object moving upwards and falling back to the ground. So it means initial positive direction is upwards. So if the object moves upwards and it falls back to the ground, so upwards is going to be positive and downwards is going to be negative as far as velocity is concerned. So upwards, it is projected with an initial velocity which is not 0. So the graph, this cannot be equal to 0. But at the maximum point, at the highest point here, v equals to 0. Then now it falls, it moves in the opposite direction. So if upwards is positive, downwards should be negative. So the line should go to 0 because this is at maximum point. This is at maximum height. At maximum height, v becomes 0. And then it changes direction. So when it is changing direction, here velocity increases. On the left-hand side, velocity decreases. Here, velocity increases when the object is falling. So this part here is moving downwards. Here it was moving upwards. So here velocity decreases when it is moving upwards, yet here velocity increases when it is moving downwards. And in lesson 2, we saw that whenever the line moves away from the x-axis, whether in a negative or positive direction, the velocity is increasing. So here the velocity is increasing in the negative direction or in the opposite direction. However, you notice that it's a straight line throughout, which means the gradient is constant. So the acceleration is constant. So if I was to sketch a graph of acceleration against time, it's going to be a horizontal line. However, the gradient is also negative, so this should be below the x-axis. Whether the object has gone up and it has come back, it is a horizontal line below the x-axis. Whether the object was falling downwards and it bounces up, it was a horizontal line above the x-axis. So it just depends on the initial direction of motion of the object. So the acceleration remains constant and negative if the object was initially thrown upwards, even when it falls back to the ground, since gravity acts on the object downwards. So the acceleration remains constant. You even notice that if I find the gradient of this part of the line is the same as the gradient here, and still negative. So the acceleration remains negative. You must have noticed that it was positive and constant when the object initially falls, even if it bounces. We have seen that previously. So you should be able to play around with these graphs. I have a short self-check for you to think about. A steel ball falls from rest through a height of 2. So from rest means initial velocity equals to 0. Through a height of 2.10 meters, an electronic timer records, so this is going to be S or H. An electronic timer records a time of 0.67 seconds for the ball. Calculate the average acceleration of the ball as it falls. So you have initial velocity, you have the displacement, you have the time. It is falling. So S equals to ut plus a half at squared. But we don't know acceleration. You can check a v squared equals to u squared plus 2as. You know the initial velocity. Of course, the acceleration is g, so I don't need to waste my time here. Acceleration is equal to g, which is 9.81. So I don't even need this. So calculate the average acceleration. What is this? A steel ball falls from rest through a height of 2 meters. An electronic timer records a time of 0.67 seconds for the ball. Okay, maybe the acceleration is not 9.81 because it's what we are finding here. So if the acceleration is constant, let me check. We have S, we have U, we can find the acceleration. So let me just find acceleration from that equation. S is 2.1 equals to initial velocity is 0, so this becomes a half times the acceleration we want times t, which is 0.67 squared. So this will be 2.1 times 2 divided by 0.67 squared. So this is 9.4. Suggest reasons why the answer is not exactly 9.81. So maybe there is air resistance which reduces the acceleration, or air resistance delays or delaying release of the ball if it is not automated, because you may not really be as you may start, because you are starting the stopwatch as at the same time as you release the ball. Maybe you delayed releasing the ball. Or we could also expect it to be greater than 9.81 if you add a force onto the falling ball in that case. So air resistance delaying the release of the ball could be affecting the value of G. In an experiment to determine the acceleration due to gravity, a ball was timed electronically as it fell from rest through a height of h. The times t shown in the table below are obtained. Plot a graph of h against t squared. So you should be able to plot a graph. Of course, this is going to be, I think this is going to be a straight line of best fit. You should draw the line of best fit. For h against t squared. From the graph, determine the acceleration. So we saw that the gradient, because we are using h equals to a half gt squared, so the gradient was equal to g divided by 2. So you could find the gradient, the acceleration from 2 times the gradient. Comment on your answer. So if the answer is 1.6 like I found, this object is not falling on the earth, it might be falling on the moon, because the acceleration of free fall on the moon is approximately 9.81. I mean approximately 2 or approximately 1.6. You can also verify that. So I plotted the graph, I think, or I have the graph here. You can just try to check the graph, or you can plot your own graph on a graph paper and verify. So you plot the graph and draw the line of best fit, which should go through the origin. Then you try to find the gradient. You just choose two good points and use them to find the gradient. You draw a right angle triangle, remember. Use them to find the gradient, and remember the gradient is equal to g divided by 2. So I tried that and I got 1.6. And lastly, let's try to explore the motion of a skydiver. Somebody maybe who is falling off out of the plane, who is falling from the plane as illustrated here. So we are considering a skydiver who is falling out of a plane, or who is falling off the plane as illustrated here. Initially, when it's just falling, like if we consider the example for the dog, initially when it's falling out or is falling off the plane, the air resistance is initially 0, but as it's falling, or as it continues falling, the air resistance goes on increasing. And when he opens the parachute, of course, the air resistance becomes even bigger. So how do we sketch how the graph of their motion look like? In that case, how the graph of their motion look like? So for a skydiver or a parachutist jumping from an aeroplane, and who sometimes later opens the parachute, the graph would look something like this. Initially, before opening the parachute, is still accelerating, so there's an acceleration somewhere. So up to some point here, of course, is accelerating before opening the parachute. The air resistance on him is increasing. So until a point here, the air resistance, the force due to air resistance is equal to the weight for the first time before opening the parachute. So the force due to air resistance is equal to the weight. So we have reached terminal velocity because the acceleration is 0. but this velocity is very high. This terminal velocity is very high. Then, when he opens the parachute somewhere here, what happens to the force due to air resistance? So when he opens the parachute, the force due to air resistance, because now the parachute has a large surface area, the force due to air resistance now exceeds the weight, which means now the acceleration is in the opposite direction to the motion, or the resultant force is in the opposite direction to the motion. And in that case, the person is going to decelerate. So because the force due to air resistance is equal to the weight, the acceleration is going to be negative. In other words, it's going to be a deceleration because the resultant force is in the opposite direction to the motion. The resultant force is going to be upwards, yet the motion is downwards. So this person is going to decelerate. So he will decelerate very rapidly. That's why you see that this line is very steep. He will decelerate very rapidly until they reach a terminal velocity, which is going to be a very small velocity. So here again, when they decelerate rapidly, it means, remember the weight does not change. When they decelerate rapidly, it means the speed decreases. And again, when the speed decreases, the force due to air resistance again decreases. And when it decreases again, it becomes equal to the weight. So here again, force due to air resistance becomes equal to the weight. And again reaches terminal velocity. So that is what exactly is happening. And then of course, rapidly lands to the ground. So that is going to be the graph of the graph representing or describing the parachutist's motion. Okay, so I want you to note from that motion that air resistance increases with the speed. That is very important. And in fact, the force due to air resistance is directly proportional to the square of the speed if the speed is for large values of v. Of course, for very small values, the force due to air resistance is almost directly proportional to the speed. A small dense object like a steel ball or a steel ball bearing has a high terminal velocity because of a smaller surface area. And a light object like a raindrop or an object with a large surface area like a piece of paper has a low terminal velocity. So when we open the parachute, of course, we are going to reach a lower terminal velocity because that's why the parachutist rapidly decelerated to a lower terminal velocity. And then at this point, the parachutist could be able to move with that constant velocity until he lands. So when he steps out of the plane, the vertical velocity is 0 initially. So the air resistance is also 0. So here, vertical velocity is 0, the air resistance is 0. When he just steps out of the plane, this means the only force acting here was the force due to gravity, which was the weight. So the acceleration here was equal to only g. As the velocity increases, the air resistance also increases. That is in the second case. So the air resistance has started increasing as the velocity increases, which means the acceleration now becomes less than g. The acceleration decreases. So the air resistance also increases, which reduces the net force. The resultant force decreases, so the acceleration decreases in that case. So that means he will now have a smaller acceleration, less than g. At the point when the air resistance equals to the weight, that is in this case here, the acceleration becomes equal to 0. We have reached terminal velocity. So the object will be moving at a constant velocity when the weight equals to the terminal, when the weight equals to the force due to air resistance. And when the parachute is opened, now the force due to air resistance exceeds the weight, which means now, remember the acceleration was decreasing, it has reached 0. Now if the force due to air resistance exceeds the weight, it means the resultant force is in the opposite direction to that of motion, so the acceleration is going to be negative. The acceleration is in the opposite direction to that of motion, and that acceleration is a negative value. So it is called a deceleration. So the velocity decreases. That's why we now move or decrease to a smaller terminal velocity. Again, as the velocity decreases, the air resistance now also decreases. So when the air resistance decreases, Again, it will come back and balance with the weight. When it balances with the weight, we now reach again terminal velocity. And the process continues until um, until the parachutist or the skydiver now lands on the ground. So here he has now landed onto the ground. So that could be a good graph for us to explore or understand the motion of a skydiver or any object moving off a plane, or a parachutist who opens the parachute at some point. And I think this should now summarize the end of lesson 2. It has been quite longer than I expected, but it involves a lot of graphs. You must master these graphs to be able to enjoy kinematics. Until next time, bye bye.